Hey everybody, what's going on? I wanted to create this video of us going through one more time just the examples of dealing with sampling distributions of sample proportions. We want to remember a couple of things that we need to be able to describe the shape, center, and spread of your sampling distribution. We know that a shape is going to be normal so long as the large counts condition is met. Your successes and failures must be at least 10. We do that by n times p must be greater than or equal to 10, n times 1 minus p must be greater than or equal to 10. The center is always going to be mu sub p hat equals p. That's the one we love. No condition to check there. That's it. Spread. 10% condition must be checked in order for us to have a valid calculation for standard deviation. So we say that our sample size, n, must be less than 0.10 times n. Your sample must be less than 10% of your population. If that's true, then you can calculate your standard deviation by the square root of p times 1 minus p all over n. Let's get to an example. Number 1, in the game of Scrabble, each player begins by drawing 7 tiles from a bag containing 100 total tiles. There are 42 vowels, 56 consonants, and 2 blank tiles in the bag. Kate chooses an SRS, and we know that stands for simple random sample of 7 tiles. And we want to let p hat represent the proportion of vowels, and this is important because that's our variable of interest. Now, before we even get into some of these questions, I'm going to write down the things that I want to know. I want to know my sample size, my population size, and the population proportion. Those are all super important. Now, my sample size, we're drawing 7 tiles from the bag, but the bag has a total of 100, so there's my population size. And then the proportion that we are interested in, this is why this part here was so important, the proportion of vowels. There are 42 vowels out of 100 in the bag, so that is 42%. Or 0.42. So, part A, can you calculate the standard deviation of the sampling distribution of p hat? So that's looking at sigma sub p hat. That's what we're going to want to find. And before we can do that, we know we need to check our 10% condition. So, we say that our sample, 7, is indeed less than 10% of our population. This is a true statement. Okay, and since that's a true statement, then we can go ahead and calculate sigma sub p hat by using that formula. This is the one formula that I usually like to write out just because it's got enough moving pieces that I want to make sure I'm getting things in the right spot. Now, I can plug things in. P was 0.42. 1 minus p then, that's the proportion of non-vowels in the bag. That's 0.58, just some complement rule stuff there. And then that's going to give us 7 in the denominator for our sample size. And what this is going to show is that we get, if I were to go to Desmos and punch this in, I'm going to leave you to do that. That gives us 0.1865. So it's that simple to be able to check that 10% condition and to be able to calculate the standard deviation. Now, next step is to look at the shape. I know I'm looking at the shape because in part B it says, is the sampling distribution of p hat approximately normal? There's my big key phrase that's telling me this is all about shape. So, with shape, we know in order to see if the sampling distribution, the sample proportion is normal, we need to check the large counts condition first. And that's saying, is our number of successes going to be greater than or equal to 10? And is our number of failures going to be greater than or equal to 10? We need to see both of these things. Are they both true? Be parentheses there, not after the 10. Sorry about that. Now, first one's easy enough. N is 7, so there are 7 tiles, and 42% of them are going to be vowels. But here's the thing. This should obviously be a false statement real quick and easy for us to see. I don't need to punch in that 7 times 0.42 into my calculator because I know that 42% of something less than 10 cannot be more than 10. So this is not going to be approximately normal because my large counts condition is not satisfied. I don't even need to check the other half of the condition, the n times 1 minus p, because, hey, we know it's not going to be satisfied. So, is the sampling distribution normal? We say no, not normal. The LCC is not satisfied. Now, part C, what proportion of the values would you expect on average here? Now, this is one of my favorites because the center is easy for us to work with. I know it's center because I am looking at the expected values or the average values. These are the key words that tell me what I'm looking to describe here as far as that sampling distribution goes. And we remember that the center of the sampling distribution, that's mu sub p hat, is always equal to p. which means that mu sub p hat is going to always equal 0.42, which tells me that in any sample of 7 tiles, I should expect 42% of them to be vowels. That's it. Let's go ahead and take a look at example number 2. All right, we have a sample survey that interviewed an SRS, again, a simple random sample of 267 college students. We want to suppose that 70% of college students have been to a party within the last month. And ultimately, the question we're going to answer is, what is the probability that 75% or more of those students in the sample have been to a party in the last month? Well, since I am talking about the probability of a sample having a certain characteristic, that means I'm going to be looking at the sampling distribution, right? And I need to look at the characteristics of the sampling distribution of the sample proportion by describing the shape, center, and spread, just the same as we had done before. So let's first look at the shape by checking the large counts condition. Well, I had a sample of 267 people, and the claimed proportion is supposed to be 70%. We are supposing that 70% of all college students went to a party in the last month. I know it's not the 75% because look at this phrasing here in the question. What's probably the 75% or more students in the sample? If we're talking about the sample, then that's supposed to be a supposed p hat. That's a sample proportion, not a population proportion. So to check our shape by looking at the large counts condition, we'll say 267 times 0.7, that's my n times p. And I know for a fact that's going to be greater than 10 just by looking at some number sets. 70% is more than 50%. And 50% of 267 is definitely more than 10, so that checks out. Now we look at our number of failures. What percent or how many would we expect not to go to a party? Well, if 70% went to a party, 30% did not. And 30% of 267, I don't know what that is off the top of my head either, but I do know it is more than 10. Because I know that 10% of 267 is 26.7. And 30% is more than 10%. So if 10% is more than 10, then 30% will definitely be more than 10. So we can say that the shape is indeed going to be normal because the LCC is satisfied. Now we look at the center of that sampling distribution, and we again know that mu sub p hat is always going to be our center, and that's always going to be equal to p. So that's easy enough, no condition to check. The last thing we want to do is describe the spread. So hopefully we have our 10% condition that's going to be satisfied. Now, the 10% condition, remember, is my sample, 267, less than or equal to 10% of my population, n. But what is n? Did we find big N? The answer is no. Well, in order for this to be satisfied, we can say that the sample must be less than 10% of the population, or you can turn it around. And that means that the population needs to be at least 10 times the size of the sample. Well, if we had 267 college students in our sample, is it safe to assume that we had more than 2,670 college students in the entire population? Are there more than 2,670 college students in the world? And I would say that is a very safe assumption to make. So we can assume that our population size is going to be large enough such that the 10% condition is satisfied, leaving us with ample room to calculate our standard deviation, where we say that's going to be the square root of p times 1 minus p all over n, and that's going to be 0.7 times 0.3 all over my sample size, 267, dividing that by my square root, or dividing that by 267 and then taking the square root of that. And that's going to give us 0.0280. And there is our standard deviation. We might think, why does that really matter? Well, there's a couple of different ways that we could approach this question. We might want to go old school, and a lot of the multiple choice questions in the AP test will ask you to actually find the z-score that represents this probability. So what we would do is say, well, what is the z-score? We know that z-scores in general are x minus mu over sigma, but now let's look at what the situation really would be related to. We're looking at what's the observed value, our sample proportion, minus the mean of all sample proportions divided by the standard deviation of all sample proportions. It's the same thing. We're just kind of changing the context of it. but it's still the same idea. Well, we remember that p hat, that was the 75%. I know that that was my p hat that we were interested in. And the mu sub p hat, that was the 0.70. And then we were going to divide this by the standard deviation, which we already found over here, but I'm going to write out the entire formula. 0.7 times 0.3 all over 267. And this is how you would actually calculate the z-score. And you might even write this out as saying this is going to be representing the probability that you have a z-score that is going to be more than that value. But that's your z. And that's it. We can use that z to calculate that probability, and we can use a z table to figure that out. And we could do that later on. But for right now, what we want to focus on is using the norm CDF kind of calculator, because that's just much, much faster for us to be able to do. Okay? So in order to work with the norm CDF calculator, we need to understand what we're working with, and we want to draw a picture. So the first thing that we would do in drawing a picture is we recognize that our shape was indeed normal. This is why we check that large counts condition, so we can see that it's going to be normal. Then I need to know what the center is of that distribution. And the center was found by that 0.70. That's mu sub p hat. So what we're drawing here is not the population distribution, it's the sampling distribution. And we found the standard deviation as well. So now we have every parameter that we need. And what we're trying to find is what's the probability that we have 75% or more in a sample. Well, 75% is going to be somewhere over here to the right. I don't know exactly where. I don't need to know. I'm just trying to understand 75% or more will be a mark to the right and an area to the right. And this is what we're going to try and find using our norm CDF calculator, where we have a mean of 0.70, standard deviation of 0.0280, a lower bound we started shading in at 0.75, and then an upper bound that's going to go all the way up to positive infinity. If we go to a norm CDF calculator that we've used a bunch of times in this class, then we will find this as being 0.0371. And that is our norm CDF calculation. Again, you do need to draw the picture, show me the formulas to show your work. And this part here is essential, where you are showing all of your work to prove the characteristics of that sampling distribution. You have to check your conditions and calculate what each of the different components are going to be. Let's take a look at another example. All right, last example that we will cover today. An online retail company that rhymes with Gramazon advertises that it ships 90% of its orders within 3 working days. So this is an advertisement. This is a claim. Any claim is going to be your assumed true proportion of a population. Okay, now you select a simple random sample of 100, so I can already write down a couple of things that are really important to me now. 90% is my population proportion. N is going to be 100. And then we see that there were 5,000 orders that were sent out in the last week. So that's where I got my 100 sample from, and that's going to be my population size. That's big N. Now, the audit reveals that 86 of these orders were shipped on time. Well, and that seems a little bit interesting, because what we would expect to see is that 90% of the orders are going to actually be on time, which would be 90 out of 100. But we didn't see that. We saw something less. And you, being the skeptical consumer that you are, makes you want to think, are they really telling me the truth, or are they advertising something a little bit false? So let's go ahead and try and tackle that. This is going to be a p hat, which we won't use immediately, but we will in a bit. This is 86%. I get that from the 86 out of 100 different orders. That's where I get that p hat equals 0.86 from. Now, here's the next thing we need to look at. If we want to find out what's the probability that we see a sample like this, where 86% of the 100 orders were not shipped or were shipped on time, then we need to describe the sampling distribution. We need to see, is it normal? What's the center? And what's the spread? So let's look at the shape. If we can't have a normal distribution, then we're kind of out of luck. We need to investigate other avenues. But we can check, is the LCC satisfied? Again, that's N times P, so that's 100 times 90. And that is indeed greater than 10, because that's going to be 90, 100 times 0.90, I should say. And then we had 100 times 10%. And that is exactly 10, but remember, the condition is greater than or equal to. It has to be at least 10. So we are satisfying the LCC, which tells us that we should have an approximately normal sampling distribution. And I'm going to draw that picture over here right now, just to kind of show you like the whole process that we are doing, and each step along the way, what's it going to tell us. So whenever I draw a normal distribution, I want to know what the mean is. I want to know what that value is. So what's the center of this distribution? Well, center, we know that that's going to be mu sub p hat, which is always equal to p, which was 0.90, which means center of that sampling distribution is 0.90. Then we need to see, well, what about standard deviation? What about the spread? Well, we need to see, is our 10% condition going to be satisfied? And in this case, it clearly is, because our sample size was 100, and that is definitely less than 10% of 5,000. So that's satisfied. Thus, we can calculate our standard deviation, sigma sub p hat. Again, this is one where I just am in the habit of writing out the formula just in case I goof something up. I want to write out that formula so that way I can refer back to it. And that's going to be 0.9 for p, 0.1 for 1 minus p, 100 for my sample. I'll go over to a separate calculator and find that the standard deviation is then 0.03. And that's my standard deviation of p hat. And what we want to do is we want to look at what's the likelihood of this happening, that we get a sample that's 86% or less. So 86% is going to be over here. And we're looking at less than that. It's going to be something over here. This is what we want to find out. Just how likely is that to happen? Okay, well, if I were to go to a norm CDF calculator, then I can see that 86% is going to be my upper bound this time. And my lower bound goes all the way to negative infinity. So here we'll kind of block everything off so we're very clear what we're doing. And now we've got a norm CDF calculation with a mean of 0.9, where that's mu sub p hat. We have a standard deviation of not 0.1, excuse me, that's 0.03. And then we have our lower bound that goes all the way to negative infinity. And then we have an upper bound that stops at 86%, because we want something that's going to be less than 86% of our orders being delivered on time. When I go to my norm CDF calculator and I punch this in, I end up with 0.0912. And that answers our question. How likely are we to get an order or a sample of 100 orders in this audit if we assume the claim is true? And that's 9.12%, or 0.0912. Now, critic looks at this and says, aha, you claim 90%, but in your sample, the on-time percentage is less than that. So this 90% claim must be wrong. And you say, well, you know what? I know a little bit more about statistics than you do. So you're going to explain why your probability calculation in A, this part here, is not giving us very strong evidence to refute that 90% claim. And that maybe Cramazon is not really lying to you. So here's what we can say. Well, if we assume that their claim is true, if we assume that 90% of all orders do arrive on time, or ship on time, we should say, there is still a 9.12% chance of seeing a sample where only 86% arrive, or not arrive, excuse me, ship on time, due to just simple random chance alone. Now, we stop to think, is that 9.12%, is that significant? The answer here really is actually no. 9.12%, while it's unlikely, this is not terribly low to make it unbelievable that this could be true. While unlikely, this is still like basically a 1 in 10 chance that it could happen. This is not unbelievably all right, so that does it for our examples for today. Thank you guys for watching. I will see you next time.